Good afternoon, everybody. Those in the room and those elsewhere. This is a hybrid meeting. For those of you online, if you look at the top left of your screen, you should see a small green shield. That symbol means that you are using the most up-to-date version of Zoom and that it is secure. Questions can be asked at the end of the lectures, but as you will be muted, please use the chat facility found at the bottom of your screen. You put these questions in the chat and then they'll be read out by Pam here, who's going to read out the questions when required at the end of the talks. I've just got a few announcements to get through. First of all, the winners of the Royal Astronomical Society GCSE poster competition, sponsored by Winton. The second prize of a £50 book token is awarded to Abbott By for the poster, Can We Throw Satellites into Space? And the first prize, a £100 book token, is awarded to Maya Charman for How to Find Exoplanets, The Search for Hidden Worlds. There's a call out for applications and nominations for the Caroline Herschel Prize Lectureship. The deadline for that is the 30th of April. More details of that are available on the William Herschel Society website. If you just Google that, you'll find it. I give notice that the annual general meeting, the 203rd annual general meeting of the Society, will take place at 4 o'clock in the afternoon on Friday, the 12th of May. That will be a hybrid meeting and more information will be available soon on the RAS website. I would also remind you that National Astronomy Meeting NAM 2023 will take place on the 3rd to 7th of July, organized in conjunction with Cardiff University. There'll be more information on the RAS website, but there is already a website open for that from Cardiff if you're interested. It's nam2023.org. That's nam2023.org, but you can obviously Google suitable combination of words involving National Astronomy Meeting 20. You know how to do these things. Okay, that's enough of the notices. Now we move on to the program for today. First of all, we're delighted to have Professor Yuan-Sen Ting, I hope I get these details right, Associate Professor at the Australian National University, who's going to talk to us about, well, there you are, that's what he's going to talk about. He's Associate Professor, as I say, jointly affiliated with Astronomy and Computer Science departments. His research endeavors revolve around the utilization of machine learning in advanced statistical inference, specifically utilizing the vast astronomical survey data stuff. Hailing from Malaysia, he was awarded a PhD in astronomy and astrophysics from Harvard University in 2017 and was subsequently granted a 4-way fellowship, most impressive, from Princeton, Carnegie Institute of Sciences, NASA Hubble, and the Institute for Advanced Study in Princeton. Wow. In recognizing of his pioneering work in AI science, he was acknowledged as a future leader by the Association of Universities for Research in Astronomy, in addition to being honored as a NASA Earth and Space Science Fellow. Recently, he's received the ARC DECRA Fellowship following his induction to ANU. And in addition to a very distinguished career, somewhat unusual thing for me to have to note of a speaker is here. I believe at one time he was a top night elf player in Warcraft 3 in Malaysia. So it's and I believe that's a first for us. So I'm delighted to introduce and look forward very much to your talk.
Thank you so much for the very, very kind introduction. Hopefully I can live up to the expectation. Okay, so I know this title seems a bit like daunting, but of course the goal today is to talk about how we can use machine learning, in particular deep learning, to advance our study of astronomy and also the statistics. So if I am not super articulate, it's because I am super jet lagged. So I just flew in yesterday. So I haven't slept for the last 24 hours. So it's okay. But the goal today is to sort of like, look, yeah, so no matter what field you are in, so there are lots of things that now we can do with deep learning, especially in the context of like statistics. So I want to talk about a specific example today, but of course the goal is really talk about like deep learning and statistics. So so most of the things that we talk about is actually from this type paper with my student last year that published in the ICML as a spotlight talk. So let's talk about the science first. So one of the main goal of astronomy is understanding how the galaxy like evolve, and we know that the evolution of the galaxy is very complex, and this can be seen from just looking at star around the galaxy, right? So if you look on the left hand side here, so what we are looking here is the galactic halo. So the star, the halo like around the Milky Way. And we can see that, so there are lots of like stellar streams. And if you look at, say, the other galaxy nearby, so on the right here, and try to image the gas with, like the 21 centimeter hydrogen fleet, you also see that there are lots of the disturbance of the gas. So what this has hinted is that the evolution of galaxy is nothing but, is very complex. And basically, it's like small galaxy merge and form a bigger guy. The way that I love to explain to my student is like this, like 1990 like Japanese anime that I like. I'm not sure that people watch this. Small guy merge and become a bigger guy. And the task of astronomy is try to do the inverse like question, right? So based on what we can observe today, we try to infer what have happened to the galaxy. Say, looking at the Milky Way, of course, what we can observe is only what we have today. But of course, the goal is to reconstruct the merger or like history of the galaxy. And because of that goal, of course, this has like motivated quite a lot of simulation in the last 2 decades. So like lots of people run cosmological scale simulation. And one of the law or the hope is that if I can find something that is very similar to the Milky Way, then I can understand what happened to the galaxy, right? So if I have the analog in a simulation. But that approaches is actually not very rigorous. First of all, of course, like even the galaxy like differ by a little bit, the merger history can be vastly different. And in fact, the galaxy like do not need to be even differ by a little bit, because even for the same galaxy, there are lots of different paths to make the same galaxy. And partly because what we can observe today is of course very limited, right? So we know the stellar mass, the black hole mass, the gas metallicity, and so forth. But these are the very crude summary statistic of the Milky Way. So it's a one-to-many inference problem. So you want to ask, given what we observe today, what are all the possible routes, instead of just looking for an analog in the simulation. And I love to think about, in the last 20 years in astronomy, for example, people have really hung up on just looking at simulation and doing large survey, as if these two things will solve astronomy. But just having both the simulation and the survey is just 2 legs of a tripod, right? So the 2 legs of the tripod will not stand on its own. What I want to convince you today is, of course, the 3rd leg can come from deep learning and machine learning, but not in a black boxy way. I want to dispel the myth that machine learning is all about black box and we cannot gain insight from that. But it's actually quite the contrary. So you can actually learn quite a lot from deep learning. So I want to talk about the goal here. So one of the main goal of any sciences is try to update our knowledge of the universe, right? So basically, you want to say, given some observation, if I can describe the likelihood, meaning that the chances that I can observe such a phenomenon, given that I have the prior, then I can update the knowledge, right? So what we call the posterior. Of course, most of you are the expert here, but of course, for people who have not worked extensively on statistics, I'd love to explain this in a simple example. So let's say you walk on the street here and you see a car. How do you estimate the price of the car, right? So you need 2 things. One is the range of the prices that you think is reasonable, so what we call a prior. But also you need the likelihood, meaning that given a price, you need to have models that describe what are all the possible cars. If you can write down the likelihood, then of course, to infer the price is just like reading out from the likelihood. So this is, of course, a tautology, even based on like himself who invented like Bayesian and statistic thing. This is a tautology. But in practice, in many like physics that we care about, not only in astronomy, in particle physics, geophysics, quite often like Bayesian and statistics are not done because for good reasons. So one of the reasons here is that you need to describe the likelihood. And for many observations, we simply do not have the analytic model to describe the likelihood. So if you lack the analytic like models, then your observation live in a very high dimensional space, right? So take an image, for example, you have 512 times 512 pixel, then you're talking about 25,000 dimensional space. So the challenge that has been how do you describe a very high dimensional likelihood? In many cases, we can only simulate, but we do not know how to describe them analytically. And this has important consequences for astronomy. So what is shown here are all the paper on the Astro archive, and the highlighted in blue are the paper that uses Bayesian statistics. So you can see that, so there are a few stronghold, I call them the stronghold of the statistics. So they are like cosmology, like pulsar, and exoplanet like transits, because these are the very few regime where we know how to write down analytic models. Our human brain are not too bad, so you can write down the models, so you can do the statistics. And interestingly, these are also the regime that won the Nobel Prize. But for a lot of astronomy, they are equally interesting. But doing proper statistics has been really, really hard, right? Including the turbulences, star formation, and also the galaxy evolution that we talk about. In fact, this scenario has also bifurcated astronomy, right? So in many places like Berkeley, for example, you have two sub-departments in astronomy. So on the one hand, you have the rigorous, serious astronomer, right? So they do cosmology. So this is the regime that is more like particle physics, because the model is very clean, so you know how to do the statistics. But there are lots of things that are very non-linear, non-Gaussian, because they are very complex. And this is the classical astronomy that are more like biophysics, right? So we seem to be content with only a qualitative understanding of the system. So what has really changed in the last few years is that it seems like we can bridge the gap. So deep learning can do a lot of stuff, but one of the uncontested application in science is understanding how do you do statistics for very complex phenomenon that you cannot write down the likelihood. So which I want to discuss with you today. So it comes down to, more technically speaking, how do you describe a very high dimensional a probability distribution function? And the breakthrough here is actually the advancement of what we call the deep generative models. So this is of course a very technical terms. So they might, what is this? So if I say ChatGPT is a deep generative models, they're like, this might be interesting, right? So let's talk about what is generative models, where we are at, how does ChatGPT works, and what does that have to do with science, right? So let's talk about what are those first. So as I have explained, as the name has suggested, the goal of the generative models is to generate, meaning that if I give a human prompt, just like in ChatGPT, it will give you the responses that will satisfy the prompt. So here is also from OpenAI. So this is called DALL-E 2. So of course you have seen a lot of this for artificial intelligence, generated arts. So it will generate all the images that will satisfy the prompt. In fact, it also capture a tourist that look into telescope in the wrong way. So you might think this is cute, but what does that has to do with science? But to understand what does that has to do with science, what is to understand how does this thing works? The simplest way to think about generative models is really a density estimation of problems. So you go onto your Instagram and download all the images and the caption. So you have a training data. And the goal of the AI is actually try to describe, sorry, I go too fast. yeah, okay. So the goal of the AI is to describe the distribution of this object. This is, of course, a schematic, right? Because both X and Y axis can be millions or billions of dimensions. So the images can, of course, live in a very high dimensional space. And assume that, let's presume that we can do that. Then the generation become very simple, because for any prompts, it's just equivalent of saying that given X's, I want to read out all the possible Y's. And this is also why ChatGPT in principle is not a plagiarism, because you are not searching for things that exist. You are sampling from the distribution of words, right? But technically speaking, what this means is that all the generative models, statistically, you are learning a conditional distribution. Just that the conditional distribution live in a very high dimensional space. Like if you see this connection, then like as a statistician, you should be very excited, because this is exactly what we need for a long time. Because for many cases, what we are lacking to do statistics is how to describe a high dimensional distribution as the likelihood. So you can do a lot of things, including like explaining the cosmology, but you can also do something that are more difficult, including like describing the distribution of graph, which I will explain today. So, but before I go into more technical thing, I want to talk about the idea of generative models come a very long way. So in the 1970s and 80s, the dream of all the statisticians is to describe this very complex distribution. So it comes in the name of what we call approximate inference. In fact, now I teach students about the approximate inference in classroom, but many approaches has failed, including some of the early day of deep learning. Meaning that in 2015, things are still not working that great, right? So you think about the older model, we call it dated model, meaning that the model that is in 2020, those are not working that well. So even things that are become very popular in media, like the GAN, the generative adversarial network, those are not good enough to do science. First, I need to explain what is GAN. So I explain why it does not work for science and what has changed. So what is GAN? So GAN is this simple idea that, so maybe what we should do is to train two machines, right? So if I want to make human faces, I can train a generator to make mock human, and a discriminator that try to decide if something is real or not. So essentially, you are letting the two machines to play a ping pong game, and hopefully both of them will get stronger over time, and hopefully that the generator will learn to generate the distribution of all the human faces. But this never actually works, right? Because this ping pong game is very lazy. So there's no incentive for the machine to learn the whole distribution. Meaning that if I want to pass the Turing test, I just need to make one human, right? So if I can make one human good enough, I will just keep making the same human again and again and again. This is why even in 2016, we can look at very realistic AI generated arts. It typically only captures a part of the distribution, which is bad, right? So if you want to make inferences, you need to understand all the cosmic variance, all the possibility in order to make the correct inference. So what has changed and has powered things like ChatGPT or the DALL-E 2, Midjourney are really the idea of how do you develop an AI that is more principled. So I will not get into the technical details here. It suffices to say that some of these new models, like the normalizing flow or diffusion models, are really more resilient to this problem of mode collapse. So you can actually capture the distribution more robustly, and you can also mathematically show that it's actually that is the case. So this is great. So assuming that you can do that, right? If you trust me, we can do that, then making inference become quite straightforward, because now instead of a text prompt, you are running a lot of simulation with different cosmological parameters. Each time you will generate a different universe. I can summarize all this knowledge in a distribution. So now if I observe something, this is equivalent of, so you can use this as a surrogate for the likelihood, and therefore you can infer the posterior. what has changed here is that you are really using all the data in the observation. So we are not compressing the information. So what you see is what you get. So you just say, given any images that we see, we can make the inferences directly in the raw space. Or more simply put, right? So once you have this like drawing a distribution for any like given universe that you observe, you can read out the posterior right away. So you might think about this is good, right? So people have been doing that for cosmology like that for a while, and people show that this is really like powerful because you are not limited by your knowledge to how to process the signal. You just use the signal as it is. So the images is easy, text is easy because you have seen like ChatGPT. Actually, like for a machine learning practitioner, we are really not impressed by ChatGPT because we know that this is already happening even a few years back. It's just that the engineering has become like better. So what is left here? I think what is really left here is that it opened up the windows, but it does not really describe all the mathematical object that we care. So for example, one of the things that we care a lot in astronomy is actually graph, right? So we do not care too much about the images, not too much about the text, but what we care about is actually a graph. Why this is the case? Take the simple example of the merger history of the galaxy. If you say fix a time, let's say 10 billion years ago, what you care about is not really about individual galaxy, but rather the relation between the galaxy. So in this case, the more natural thing to do is to describe the graph. But graph is really a very, very complex object. It's much more complex than the images for few reasons, because the first of all is that the dimension is not fixed, right? So you can have 20 galaxy and merge to form the same galaxy. You can also have 10 galaxy merge to form the Milky Way. So first of all, you need to know how to deal with the changing dimension. But you also need to deal with a loss of the symmetry groups, because graph have quite a lot more like symmetry than an image. So you have the rotation, you have the flipping, but you also have the indexing of the graph, right? So there is no fixed indexing, unlike the images, right? So this gives you n factorial type of graph that are exactly the same graph. So this has been the challenge of how do you deal with this object. And this is why classically, even before like 2020, most of the graph neural network are really limited to the simple case of classification, right? So you throw in a molecule and decide if this solves COVID or not. So this is actually a simple case. A more challenging case is do the reverse question. Instead of asking if a molecule solves COVID, you want to ask, I want to solve COVID, give me all the molecules that could work. So COVID is bad, but one of the good things that came out from that is that people care more about this question, right? And it really have pushed forward what we call the generative graph models. So technically speaking, what we have learned over time is that you can actually teach the machine about the symmetry of the graph. So by showing the path for them to learn and not to learn what, you can actually make sure that you can do this type of thing. So what does that have to do with astronomy? So one thing that we have shown is that, for example, in the simulation, you can look at all the galaxy at high redshift, meaning that 10 billion years ago, you have the outcome of the galaxy. And in your cosmological simulation, you have many such pair. What you can do now is actually learn the distribution of all the graph. You might think, well, why do you spend so much time to think about this? Because this is exactly what you need to answer the one-to-many question, right? So for example, now I can ask if I want to form the Milky Way, give me all the progenitor that could form the Milky Way. Just like you give ChatGPT a prompt, you give you all the possible responses that will satisfy it. So it's not limited to what you have generated in the simulation. So you're learning from the knowledge of the simulation, but you're going beyond that. You are generalizing the knowledge. So, technically what we have learned is that the conditional distribution between the outcome galaxy and the progenitor. So we show that you can condition on things that we think we can measure today, including the gas metallicity of the galaxy, the stellar mass, and so forth, and try to give all the progenitor that will satisfy the prompt. And this leads to a lot of applications. So the following will be slightly more technical, but of course, it's for the astronomer in the room. So one thing that is quite exciting is how do you find outlier in the configuration space, right? So think about if I am the alien, I might not change my star, but I might align the star to form SOS, right? Or move the star around. So how do you know the configuration of the object are not reasonable? Classically, this is a very hard mathematical question, right? But now if you believe that we can describe the distribution of graph, then you can ask if something is inside the distribution or outside the distribution, right? So if this is some unicorn or not. So as a proof of concept, we show that this actually works. So we started with a configuration that is in the simulation. So we know this is a normal configuration and therefore has a high likelihood, meaning that it's inside the distribution. So let's say I am the alien. I can push a galaxy left and right. So configuration-wise, it would look quite normal by eye, but the machine will know that this type of configuration would not be generated in your simulation, no matter how many times you run the simulation. Just like if you have a good trained ChatGPT models, you will know which sentence is slightly off. And this is by this way you can look for outlier in the configuration space that we couldn't do in the past. The other application is what I have mentioned a lot, which is doing proper statistics. So you can use this as a likelihood and infer what the galaxy would become. So for example, if you observe some high-redshift system with James Webb's, right? So you want to ask what the galaxy would become. And what you can do now is that once you have summarized the distribution, you can ask given Y, I want to read out all the possible X. So to show you one example, so here in the top right here, we are showing you, let's say you assume, you observe such a configuration at redshift of 2. You can ask what the galaxy would become, right? So of course, this is from the simulation, so we know the ground truth, which is shown in the crosshair. And the white contour here show you the posterior that is sampled by the likelihood, meaning that we are capturing the correct posterior about what the galaxy would become. And this is what I meant by you can extend the horizon of a statistic, because classically it's almost unimaginable of how you would do a statistic with such an object, right? Like with a graph. But now with deep learning, we are able to capture things as a distribution, and therefore we can do the statistic as rigorous as what people have been doing in particle physics. But more than that, right? So you can also ask, if I want to form a slightly different galaxy, what would be the closest graph that would make the galaxy? It's just you can ask ChatGPT, you write sentences, you don't really like the sentences. Can you be more polite? So you would change the sentences by a little bit, right? So this is exactly what we can do. Once you have summarizes the knowledge of your simulation, you can tweak that and learn from that, right? So you can try to ask, if I want to make a smaller galaxy, what would be the closest analog? If I want to make a more metal-rich galaxy, what would be the analog? So, and the other application is really learning from the simulation. So we have the ability to run the simulation for a long time, but we have very little means to understand what is in the simulation. So I have read this article from Nature that's saying that we are now meta-human doing meta science, because of course the simulation know much more than what the human know. The question is, how do you actually go into the simulation and understand what the simulation is doing? And this gives you a way to do that. So let me explain this by asking, so let's say I want to form the Milky Way. I want to ask, what are all the possibilities that can form the Milky Way? In principle, I want to understand what are the correlation of all this possibility. Why this galaxy, this group of progenitor can all make the same galaxy. But this type of question is almost not answerable with the classical means. Because classically, what we have been doing is that, I look for analog in the simulation, but no two galaxies are exactly the same. So in your simulation, you will never find two galaxies that are exactly the same. Just like if you ask like ChatGPT a prompt, you can generate all the possible response that will satisfy the exact prompt. But if you just do a Google search, you will never find two prompts that are exactly the same. Because when you are integrating like over X, you are smearing out the correlation like between Y's, because you are not able to slice the simulation the way that you want. More concretely, I can show you one example here. So we are asking, what can form the Milky Way and what are the correlations between the progenitor. So if I just look into a simulation and look for the 200 closest analog, I can see some structure here, but it's very hard to make out of that, right? Because you are limited by the sampling noise. So you can run more and more like simulation, and hopefully that you land on more analogs. But that's really hard, right? You can also say, I will look for a bigger sample, I will look for more sample within the simulation, and that would not work either, because if you take a larger sample, most of these galaxies would not be the same in the first place. So you wash out the correlation. But on the other hand, if you first learn the distribution and then sample from the distribution, then you can start to see the correlation between the structure. It's just like if you ask ChatGPT a prompt and let it generate all the possible responses, then you start to see the correlation between the words that you would have to see if you just do a Google search. And this is exactly how you can start to understand the simulation like better, because you can slice the simulation as precise as you want. So I'm almost done. Actually, I'm getting too fast, but I can take more questions. So the abstract that I want to convince you today is the machine learning is actually less a black box than most people thought. So it's actually a very powerful tool to become the third leg of the tripod, where you can connect simulation with observation in a statistically rigorous manner, because technically what you are doing is summarizing things in a high dimensional distribution, which you can use that as a surrogate for the likelihood. Why that is important, I'll show you some applications, including finding outliers. You can ask what the president would say, and then you generate all the possible text. Then you can ask which one is the sentence that the president would not say. So that's the same idea. Once you can generate, then you can really ask if something is outlier or not, just by having the normal set. And this is very different, right? So in many cases, we are looking for unknown. So you do not know what you are looking for. The best you could do is to summarize what is known. And that is a very powerful way to look for unknown. So I'll show you that you can do the simulation-based inferences, meaning that you can directly connect simulation to the observation with no information loss. So you're using all the photons that you have collected and make the best inference that you can without going through the signal processing. Of course, the last thing is just how would you go into the simulation and understand what is in the simulation? How do you distill knowledge? So the best thing I love to do with ChatGPT is become my routine now. I just ask a single prompt and then just generate all the responses and looks for patterns within the responses. And this is what we can do now with science. So with this, I will stop. I know this is a very general topic. I will be happy to take question and criticism and skepticism of this topic. Thank you.
Thank you very much. I'll invite some questions. Steve Eels.
It's really nice talk, a really clear talk. I guess my question is, we already know that simulations often fail to predict observations.
Right.
Can your method actually test the simulations at the same time as you're interpreting observations?
Yeah, so this is become slightly more technical, but once you can capture the likelihood, you can calculate what we call the evidence, right? So you can have two hypotheses, and then you can integrate over the likelihood. And this is why even you're testing the hypothesis, and this is a very powerful tool. Of course, you are not looking for the correct single hypothesis, because you cannot test all the hypotheses. It's a functional space. But if you have different hypotheses, you can use this tool to understand which one actually is the better like description of the universe.
So could you take two different simulations and say,
Exactly.
okay,
Exactly.
thank you.
Another one? Can you please say your name when you get the thing?
Yeah, Ofer Lahav from UCL. Thanks for a fascinating talk. I think the view, as expressed also in talks earlier today, is that probably one can no longer do cosmology without machine learning. So you're preaching the converted, but the question is how far to go and how revolutionary would that be in cosmology, say, compared with protein folding?
Right.
So to be, just to ask a very hypothetical question,
right.
If we give all the data to date
right.
in astronomy
right.
to an algorithm, could it rediscover general relativity?
Right. So this is sort of like a general problem with astronomy. So to put it the best way I could is like astronomy is too simple and biology is too hard, right? So you only make the gain when you are fundamentally bottlenecked by your inability to describe the phenomenon. And astronomy is a very delicate thing because we can do a lot already. So the gain is always 10-20%. Is the 10-20% will give you some deviation that you are looking for in cosmology, who knows, right? But the 10-20% could be there. It's also I love to think about, the Roman, the telescope is $1 billion. So if you save 10%, you are saving 100 millions, right? So that's the calculation you're doing. But overall, what is really hard compared to protein folding is because the astronomy is too simple.
Astronomy is too simple. I always remember, I think Fred Hoyle was once reported to have said, well, he said, viewed at 10 parsecs, a star's basically a pretty simple system. And somebody piped up in the audience say, viewed at 10 parsecs, you'd be pretty simple yourself, Hoyle. Belinda Wilkes.
Hi, yes, Belinda Wilkes. I'm sort of following up on Steve's question, but we know that the simulations are not perfect. They don't do necessarily all the physics right. So when you're doing these comparisons, can you find the bits that are wrong? And do you understand how they're biasing your results?
Right. So this is another 1 hour talk that I couldn't give. So this is all about the inferences, right? So astronomy have two parts. One is gaining insights, and the other is making the inferences. So the talk that I'm focusing today is purely on squeezing out all the information in the inferences. The question you're asking is that how do I know which frequency is wrong, which part is wrong? Their way to do that is actually the other branches of deep learning, which we haven't touched upon. It's a very difficult thing to answer, but short answer is yes, but it's a completely different things that we're talking about here. Yeah.
Yes. Further question, Q?
Q Stanley. Will we get to a position with this that we can actually look at previous data sets which we've got and process those and extract more information and possibly pick up where the data has been misinterpreted or gone through a wrong workflow?
Yeah, so I think this is related question, but yes, so people are doing that. Astronomy, there are so much data, and in many cases we are really butchering the data because we are not doing the best statistic we could. It's not like people are not smart enough, just that the dimension is very high, or the heuristic that you come up with are not optimal. So people are doing that. They are walking back to looking at old data and squeeze out more information from cosmology. So people still, yeah.
On the flip side to that, just wondering, is this subject to wrong processing of data? Would that bias the models in any particular way?
Yeah, so this comes back to, in practice, you want to be very careful because this type of blind likelihood will not tell you about the foreground, right? So if you have some foreground, you want to censor out some of the frequency, this is very hard because they're all merged into one. So there is always a compromise between how expressive the models can be and how much you have the control to censoring out some of the information. So there are tools to do that. You can actually have a hybrid that, it's always there's no pure learning. There are no pure modeling. It's always a spectrum. And now we are really pushing the whole spectrum, and we actually know the tool to slide the slider where we want. And that is really quite liberating.
Thank you. I believe there's a question online.
Yes, so the question comes from Muthaya Ravichandran. And the question is, how can the error rate of a simulation be decreased?
Yeah, so this is really about the hypothesis that testing, right? So no simulation is correct. There are a few ways to tackle that question. I think the better way to do that is really do the hypothesis that testing. You can run a different simulation and figure out which one is actually more correct. Somewhat like limiting. The other approach is really doing deep fake, which I didn't have shown. You can actually like morph one simulation to the other. So I actually wrote a paper like use deep fake to do good science. So you can actually like use the statistical method, meaning that I want to find a minimal path that morph one distribution to the other. Is that interpretable? No, but is that like mathematically sound? Yes, because there is a minimal path that morph a high dimensional distribution from one space to the other. So you can do auto-correct for things that do not included in the simulation. Yeah.
And another one?
And this next question also comes from Muthaya Ravichandran. And it's, could the simulations have predicted the presence of dust without the BICEP 2 experiment that changed inflation cosmology?
I think that will be hard. So you can probably figure out something is off because the likelihood seems too low or something. But in the regime that we're talking about, you're always testing the hypothesis. So you need to have the hypothesis and test the hypothesis. But what is really like, if you look at sort of the B mode, P, the inflation modes, those are things that are highly like Gaussian. Like we know how to describe that quite well, like analytically. So this is not what the biggest gain is, which is like, this is why I hate to talk about like I do work on like cosmology because like these are people that they are more like receptive, but the gain is small. What is really gain is big is like star formation or galaxy or like the turbulences or human, right? So those are the biggest gain.
Any more questions in the room? There's one over here, and we'll come back online in a moment or two. Simon Minton.
Yes, Simon Minton, Cambridge. I've got a simple-minded question because I like to look for analogies and crossovers. So, is there any overlap in terms of philosophy and simulations between the work you're doing and, for example, simulating global climate change or simulating the weather or
Right.
simulating a national economy?
It's a very broad question. So one thing that I would love to think is very like connected to philosophy, which I often ask myself, which is what is understanding, where physics stops, right? So, and for different people, they have very different answer. So for biophysics, there is almost like very little theory. The goal is to do the inference. For the particle physics is always the model that testing. But for astrophysics, because we are crossing like 17 decks of things, and we are blurring the line, right? So we are blurring the line about, like, are we learning something or is it good enough to do like inference? And the word understanding, I think, is too limiting to express what we are doing as a physics. And there's no like consensus, and there's no education about what physics is about. I was not taught about what physics is about. And astronomy is actually at this cross section because it's between particle physics and biophysics. And now you suddenly connect the two ends. And then you can ask, which part become not physics? I think that's sort of the philosophical question.
Okay, well, I believe the presidential lecture this year might touch on the thing, what do we mean by understanding in astronomy? So good. Something else online?
Yes, this question comes from anonymous attendee. And it's, can a set of responses from one or several AIs be used to train another AI, or would it simply be garbage in, garbage out?
Yeah, I think the question is, you are not gaining effective sample. You can always make more sample from the distribution that you have learned, but the uncertainty of the distribution is limited by the training sample that you train on. So you can like generate more sample. It does not make the question, like the hard question here, the hard mathematical question here is, how good is your estimate of the distribution? Like does it decreases with 1 to the log n or 1 to the square root of n? Like no one knows. But that question, like you can just make more sample and retrain with that would not help. Just like ChatGPT can spew like garbage and retrain on that. It would not help. But what would help, of course, is sort of like human like influencing. So if you know how ChatGPT is trained, is that the human ranking actually is a big part. So you rank the responses, and then your penalty function depend on the ranking. So that will give you more sample for people to rank on. But for science, it does not matter. Yeah.
Thank you. Any more questions in the room? One at the back there.
Ranjan Balakumaran. How do simulation machines, how do they recognize higher dimensions, as in dimensions that I wouldn't understand?
Yeah, I have another talk this morning that talked a little bit about that. So there's no magic here, right? So what happened here is that all the neural network that you're doing are making some assumptions. So what we call the inductive like biases. So what you should think about is like you have a 3D sphere, you would think that how could I sample a very high dimensional sphere? But if you know that the sphere is a sphere, then you are collapsing all the data into one dimension. So what is really under the hood, why network can evade the curse of a dimension is because you are making the assumption on symmetry of the data. Same for ChatGPT and the languages. Some of these assumptions are weak. So we call that like approximate symmetry. It's not like really a symmetry groups, but you're making an assumption. So this is why I always say that no machine learning is pure learning. It's always modeling. You're always assuming the symmetry group or something about the data set. That is why you can solve the dimension. Yeah.
Okay. Are we done? Okay. Well, can we thank very much indeed? Thank you very much. Now, our next talk is by Nicolene Weil, Research Associate at NASA Goddard Space Flight Center. And the title will appear in a moment. It's the Grand Challenge Questions of Solar Wind Physics. Dr. Nicolene Weil is a research astrophysicist at NASA's Goddard Space Flight Center with expertise in solar coronal and solar wind physics. She is a winner of the 2018 NASA Early Career Achievement Medal and was the 2018 recipient of the Karen Harvey Prize awarded by the Solar Physics Division of the American Astronomical Society. That's SPD-AAS, and she currently serves as the SPD-AAS Vice Chair and is the mission scientist for NASA's polarimetry mission for the corona and heliosphere. So it gives me a great pleasure to ask her to give her talk. Thank you.
All right. Well, thank you all for coming, and I'm so excited to be here. Yes, I'm going to be talking about the grand challenge questions of solar wind physics, all in 50 minutes. So thank you, yes, to the Punch team and the Parker Solar Probe Whisper team. Okay, let me start actually. Here we are. I've gotten to come to the UK a number of times to see professional colleagues and meet people. And so it's so nice to be back in the UK meeting with professional colleagues again. This is the first time I ever got to come to the UK. This was a meeting in Cambridge, and I was in Cambridge earlier this week speaking to them about this topic. Let's see, is there a pointer on here? Yes, that's me. I was just a young postdoc, and this was I think one of my first foreign professional conferences, and it was really important because I got to meet a lot of really great colleagues who we collaborated later. This is the most recent time I was in the UK before this trip here. This was up at St. Andrews, and I know those are a bunch of backs of people's heads, but you might recognize some of your colleagues in there. I think Peter, one of those heads is Peter's. And maybe Eric was there too. Yeah, I think one of those heads is Eric's. Anyway, so like I said, it's just so great to be back here. Okay, how does the solar atmosphere create the solar wind? The atmosphere of the sun, we call that the solar corona. It is extremely hot, a megakelvin. Is not bound to the sun, and it flows away at hundreds of kilometers per second, and we call that the solar wind. So how does that plasma, how is that created, and how does it fill the solar system or the heliosphere? And how do those resulting structures, because of how the solar wind is created, how do those structures then drive geospace? And geospace means the Earth, which we live here, the Earth and the Earth's magnetic field and the magnetosphere. So that's the very big picture of what I'm talking about today. So I'm going to start with some research that I did actually in graduate school. A lot of the times, the solar wind structures are periodic, and they're periodic in density. And so from the perspective of the magnetosphere, that's a dynamic pressure periodicity. And they drive oscillations in the magnetosphere by literally squeezing the magnetosphere and then releasing it. And then the next structure comes along and squeezes the magnetosphere. That was what that cartoon movie showed there. So here's the Earth's magnetosphere. And if we have a satellite here measuring the magnetic field and a satellite out here measuring the density of the solar wind, the satellite out here will measure the density increase and decrease periodically. And then the satellite in here will measure the magnetic field in the magnetosphere increase and decrease as it's being squished and then compressed and then released. And here I'm showing an event of this occurring where in the black line, we're seeing the periodicities in the solar wind. There's a long periodicity, and then there's a shorter scale periodicity on top of that. And then the gray is showing the magnetosphere response to that. So this is, if you're familiar with the big solar explosions on the sun, the coronal mass ejections, this is not one of those. This is like quiet time, ambient solar wind, and yet we're getting this driving of the magnetosphere. What I'm showing over here on the right are spectra computed from these time series here. What you can see is that at low frequencies, sort of like an hour, 20 minutes, 10 minutes, the spectra of the magnetosphere and the spectra and the solar wind follow each other almost identically. This driving happens at multiple frequencies. And then at higher frequencies, up at about 4 millihertz or so, the magnetosphere kind of starts to do its own thing. Now, at the time that we did this, a lot of the magnetospheric physicists thought that the magnetosphere was always kind of ringing like a bell. It had its internal modes, and that the frequencies weren't caused by the solar wind. It was all internal dynamics from the magnetosphere. But we should know that, I mean, of course, the magnetosphere does do its own thing sometimes, but that actually the solar wind was driving these periodicities. And so then people said, well, okay, maybe that was just the one time that ever happened. And so we did statistics of 11 years of data, 11 years of analyzing solar wind data and magnetospheric data. There it goes. This is another cartoon just showing the same thing, but another cartoon view. Here we're imagining that the density, the density structures, there we go. The density structures are advecting with the solar wind, and then they're compressing the magnetosphere as they advect past. And for example, here, if we've got a 150 megameter structure, and if it's advecting with the solar wind at 400 kilometers per second, that will show up as a 2.5 millihertz wave from the perspective of the magnetosphere. So we looked at 11 years of solar wind data here that was impacting the magnetosphere, and 11 years of magnetospheric data. And we counted up every single time we saw in 6-hour chunks of data, we counted up every single time we saw a periodicity, a discrete periodicity, what that periodicity was. And what I'm showing here are tables basically of occurrence enhancements. So periodicities that kept showing up over and over again. It wasn't a smooth distribution. There were particular frequencies that showed up more often than others. And that's what this table describes here. And we did 11 years of data, partially because that's what we had, but also partially because that's a solar cycle. And so if those frequencies shift, you might expect that to follow the solar cycle. And in fact, that's what we observed. So for example, we see 2.3 millihertz show up a lot, but it kind of evolved with the solar cycle. Sometimes it shifted over and came back. And They weren't identical in the magnetosphere, but often we saw the same frequencies in the magnetosphere. Again, at around 4 millihertz, then the magnetosphere kind of starts to do its own thing and is less often driven by the periodicities in the solar wind. And then the final thing we did is we actually asked not just which periodicities, but how often were the exact same periodicity found upstream in the solar wind exactly with the magnetosphere at the exact same frequency. And what we found was that it was 54% of the time. So 54% of the time that the solar wind had one of these periodicities, it directly drove a discrete periodicity in the magnetosphere. All right, so these periodicities in the magnetosphere are from the solar wind. Well, now we just have a new question though, which is why would the solar wind have periodic density structures to begin with? Why would the sun make solar wind that has particular scale sizes? So that's how we go back to our big picture question of how is it that the sun makes the solar wind in the first place? And then how are those structures that are created through those processes, how do they get to the Earth? And when they get to the Earth, what are they doing to geospace? And we know the answer to this question in a general sense and on large scales and long time scales. And I'm showing two figures here that illustrate sort of the general understanding that we have. Here I'm showing an ultraviolet image of the sun. So in ultraviolet, you're seeing kind of megakelvin plasma. You're seeing the corona, but you're seeing low down in the corona. And then on top of here is a white light image of the corona, and you're seeing a concentration of, so white light is just density, that's what you're seeing here. And then plotted around it is the dial plot of in situ measurements made by Ulysses. Ulysses measured over the poles of the sun, and it measured, took, I think several years to make this plot. But what it observed is very fast wind, 700-800 kilometer per second wind, solar wind, coming over the poles of the sun. So associated with these darker regions in the ultraviolet. So they are regions in the corona that are less dense and a little bit cooler. And at the equator, slower wind, 300-400 kilometer per second wind, and more variable, associated with these denser, hotter regions of the sun. All right, so that's a general understanding that we know. If we go over to this picture here, again, white light on the outside. This one is taken with SOHO. In the middle here is an image taken during the 2017 total solar eclipse that happened in the United States. I got to see the total solar eclipse. How many people have seen the total solar eclipse? Yeah, it's pretty awesome. And in fact, I should mention that total solar eclipses are very important for a lot of reasons, but as being here as the Eddington lecturer, the Eddington, of course, demonstrated observationally Einstein's theory of general relativity by using a total solar eclipse to measure the starlight shifted by the sun's gravity. And he did that during the 1919 total solar eclipse. Okay, so here we're seeing the total solar eclipse in the middle. It's still just density. And then at the bottom in the middle here, we're seeing ultraviolet 1 megakelvin plasma. And what I've drawn on are cartoon lines of the magnetic field. So roughly the sun has a dipolar field here, but these field lines at the top get dragged out and they're open, which means that only one field line is rooted in the sun and the other field line is out in the heliosphere, out in the solar system. Here near the equator, those are closed magnetic field lines, where one field line actually closes back and both foot points close back in the sun. So that's the other association, is that the fast wind is associated with these open field lines and these darker regions that are in ultraviolet, so they're a little bit less dense and a little bit cooler, whereas these closed magnetic fields are associated with the slow wind and they're denser and they're hotter. Okay, so we've known this connection for a long time. Nothing about this big picture predicts mesoscale structures, predicts the kind of structures that we saw driving the magnetosphere. And in fact, the sort of two leading theories of solar wind formation, broadly speaking, one has to do with waves, one has to do with magnetic reconnection. Both of them predict these general correlations. So we can't actually distinguish between theories just with this global long-term scale. So we have to look at the finer details. And the connection, though, between all of these different layers of the sun is time dynamic, it's three-dimensional, and there's enormous complexity that I'm going to talk about. This is a movie taken in white light again. So this is, you're looking at the density of the corona. And I've got a 2-scale EUV image here in the bottom, just so you can see what the sun, the size of the sun. So this is about 5 solar radii out to about 15 solar radii. It was taken with stereo. And what I want you to notice is that there are no quiet days on the sun. The solar wind is constantly dynamic. It's highly structured in space and in time. So this is what my research team has been quantifying. We're calling it the ground state of space weather. It's all of the space weather, all of the dynamics, the dynamic driving of the magnetosphere that happens on a day where there wasn't a big explosion on the sun. This is just the regular solar wind. Okay, and that brings us to our grand challenge questions. And we wrote a paper on this a couple of years ago. And I'm not going to go through all of the questions and answer all of them today. But what I'm going to do is just give you a sample of how my research group has attacked some pieces of these questions. And the questions, we had 9 of them, and we broke them out into 3 themes. The first theme has to do with this question of how is the solar wind formed in the first place? And we actually broke it apart into 3 different steps having to do with the energization low down in the corona versus the energization higher up, because it's highly likely that those are entirely different physical processes. And then how the solar wind is released, and that's really a question about mass. How are you getting the mass out? Theme 2 is about how to interpret observations of the solar wind, things like the elemental abundances, things like how do those structures evolve through the solar wind out into the heliosphere. And then the third theme has to do with the physical mechanisms operating in the solar wind. And if you knew everything about the sun, then a lot of these questions actually might end up be the answers to some of these questions up here, but we don't know the answers yet. But these are questions about turbulence, alphanic fluctuations, kinetic distribution, functions, and so forth. Okay. So this is just another view of the sun. We're looking at ultraviolet again. These are Go-Subi movies, and you're looking at 171 and 195. So this is about 1 megakelvin and 1.5 megakelvin plasma that you're looking at. In the corona, it's very hot, lots of dynamics, lots of structure. And so again, there are no quiet days on the sun. The other thing to note is just in this region here, just in what we're seeing here, we go from extremely collisional plasma to collision-less plasma. So the plasma state totally changes. Beta is very different down here than it is way out here. The sound speed changes, the alphane speed changes tremendously just over this region right here. You have this complex tangle of mixed polarities, closed magnetic fields down here and then out here. The magnetic field lines are pretty much radial, and you have a north pole and a south pole and a current sheet between them, and it gets a little bit simpler. And observational types. You saw that in some of the images I showed already. Down here, it's easier to see the corona in ultraviolet. As we look further out, it's easier to see it in white light, but you're looking at slightly different things, slightly different aspects. And then when you get really far out, then really the information we have is in situ data. And so connecting these different observations is part of the challenge as well. Okay, so our first question is, from where on the sun does the solar wind originate? And really, this is the coronal heating question. Why is it that the solar corona is so hot? And the reason that we start with this question is because this is the energization of the plasma low in the corona. So just broadly speaking, I already talked about this a little bit. Coronal holes are a little bit less hot. They're more tenuous versus these things that we call coronal streamers, where the field lines are closed, they're a little bit denser and they're a little bit hotter. And because the field lines are closed and because they're hotter, probably that's different physics heating those two regions. And you can see this streamer right here is this white light, dense, bright feature right here. This streamer over here is connected to, in my little cartoon here, is connected to what we call an active region. So these are these bright spots on the sun in ultraviolet because they're hotter still, they're denser still. And again, probably heated by a different mechanism than what heats the coronal holes up here. Or at least operating in a very different regime, even if it is the same physical mechanism. And so the plasma coming out of this active region will look very different than the plasma coming out of this coronal hole. And so again, this is the coronal heating problem. So what heats the solar corona? The energy release, even though we've zoomed way in from galaxies, and we heard earlier about how hard it is to understand galaxies, we've zoomed way in, but even with our own sun, with all of the data we have about our sun, even still, we cannot resolve, we do not have the instrumentation to resolve the energy release, the individual energy releases in the corona. So there is some sort of energy release in the corona. They're below instrument resolution, they're below instrument sensitivity, and even if you could see it, because the ultraviolet light is optically thin, there would be many of them along the line of sight. So we can't see individual energization events. And then after the energy release happens, on your flux tube, then there's a giant black box of things that are difficult because again, we're not directly observing them. The magnetic field lines that come up through the photosphere, through the transition region into the corona, couple those regions of the atmosphere. The chromosphere is orders of magnitude cooler than the corona, and then the photosphere is a couple of orders of magnitude cooler than the corona, but it's all coupled. And so when the heat gets deposited, when the energy gets deposited into the corona, then thermal conduction rapidly smooths out any evidence of that energy deposition. So that spatial information is gone. And the thermal conduction sends that energy down into the chromosphere. The chromosphere now heats up and fills that flux tube with mass. And so now, after all of that has happened, now we can finally actually see this flux tube after all of that has happened. So this is what we're seeing when we're looking at these images here. We're seeing the thermal emission long after the energy has been released, long after the energization. So it's actually very difficult when looking at these images to understand and back out actually what the energy release was in the first place. So one thing we can do though, we've looked at light curves with Solar Dynamics Observatory atmospheric imaging assembly. Those are EUV images, and AI has 6 different channels, 6 different EUV emission, so 6 different temperatures. What I'm showing here on the left is that if we take a model of a flux tube and give it energy in the first, I think we did it in the first 50 seconds, so way at the beginning here, we give that flux tube energy. It is not emitting yet very much because it's pretty tenuous. Then after that energy deposition happens, then the thermal conduction sends that energy down into the chromosphere. Then that chromospheric material gets hotter and becomes coronal material and fills the flux tube. And then we actually can start to get emission in some of these channels. And so what I'm plotting here is the predicted light curves from one of these nanoflare events, one of these energizations of a flux tube. And you don't see it for the first, I don't know, 1,000 seconds. You don't even see it, even though we heat it in the first 50 seconds. So you don't see it for a long time. Then all of a sudden it shows up in the hottest channel. In this case, it's a 3 megakelvin channel. The green was 3 megakelvin. Then you see it show up in the next channel. That's the blue channel here. Then you see it show up in the next channel. That's the orange channel here. And then it sequentially cools down each of the 6 channels. So you can at least see this part. And you can automatically test how often this has happened and if it's happening by just cross-correlating the light curves. And so that's what I'm showing here. If you cross-correlate 2 of the light curves, you'll get a peak cross-correlation just exactly at this cooling time. And by looking at all of them, you can actually track if this post-nanoflare cooling is happening. So that's the first question, is it happening at all? And then you can also look at whether the plasma cools fully or whether it stops cooling, whether it never gets to the coolest channel because the plasma actually has been reheated and it shows back up at a hot temperature. And what I'm showing over here is actually, this was for 1 flux tube, but we've actually run it for thousands of flux tubes along the line of sight. And you can still pull out a net time lag because this heating phase is basically invisible. All right, so we did this cross correlation on a pixel by pixel basis of these 15 active regions. So here we are, we have 15 different active regions. I'm showing them in ultraviolet light. There are these concentrations of magnetic field. They're very bright, they're very dense, but we're very low down in the corona. So we're still just asking this first question of energization low down. And on a pixel by pixel basis, we tested whether or not this nanoflare, post-nanoflare cooling was happening, and if so, how much. So these are maps from all 15 of those active regions. And the maps are color-coded so that this post-nanoflare cooling is colored red, orange, or yellow. And if there were something different going on, some slow heating that we were able to see, that would show up as green or blue. But we really don't see that, maybe a couple patches here or there, but mostly what we're seeing is reds and oranges. And then the olive green color is dynamics that have to do with the transition region itself. So this is a transition region around the active region. And then you're seeing these active region loops exhibiting this post-nanoflare cooling. And I'm only showing one map here, one map of one channel pair. But as I said, by looking at all 6 channels together, actually we can watch the plasma sometimes not cool all the way and get reheated. And then now we have a time scale for the reheat time of the energization. That flux tube cools, say about 1,000 seconds, and then it gets reheated. So we still don't know the actual energization process, but we've at least narrowed down that it's a process that recurs every 1,000 seconds or so. And by combining these with differential emission measures, which is the amount of plasma as a function of temperature, then we can really accurately constrain this time scale of heating low in the corona. Okay, but that's just the first question. That's just how is the plasma heated in the first place when it's low in the corona? We haven't yet turned it into solar wind. To turn it into solar wind, we have to actually get it out into the heliosphere, out into the solar system. If it's already on an open field line, in my cartoon version here, then that's fine, it just goes out. But as I showed, there are lots of closed field lines. And so for that plasma to get out, the closed field lines have to reconnect. And you can do that in sort of, again, in my cartoon version here, there's sort of 2 ways to do that. You can have a long loop that sort of disconnects or blows open, or you can have what's called interchange reconnection, which is just where you have some form of closed flux adjacent to some form of open flux, and they swap foot points. And the key is that this reconnection might have nothing to do with the process of heating lower down. This might be reconnection that's occurring very high up. And in fact, we have observations of reconnection occurring very high up. And this reconnection may not be energetically important. It might just release the solar wind and might not actually introduce much energy into the plasma, or it might introduce energy to the plasma, but that's sort of the third question. Okay, so I'm going to show next some evidence of solar wind being released through this middle picture here. All right, these are images, white light images, but we false colored them, but these are white light coronagraph images. So you're just looking at electron density. Okay, this is the sun right here. It's actually the occulter disk at about 2.5 solar radii. And then we're seeing ejection of plasma at the end of one of these last closed field lines, one of these long last closed field lines, right at the current sheet between the polarity inversion. And it's being ejected and we see it come out, this blob of plasma, and we can, in this series of stills, we can follow the blob of plasma come out. It goes all the way out. And then in the next set of imagers, we can follow a series of these structures coming out off of the heliospheric current sheet, this current sheet at the end of this last closed field line. We can follow it from 15 solar radii out to about 50 solar radii. And then we lose them because they fall below the instrument sensitivity. So these are stereo data, stereo white light data. And by taking slits here, we can watch the time series of these structures advect past. And we can ask whether these structures are occurring periodically. And in fact, we have evidence that these do occur periodically, and I'll show you that in a minute. But the key is we see the reconnection, we see them being released way back here. And they don't really accelerate much when that happens. They kind of just slowly accelerate with the background solar wind. So we don't think this reconnection that's occurring way up here really is very energetically important. But in terms of the mass contribution that it's making, it's incredibly important because that's how that mass is getting out. So the point is that we start with the energization low in the corona. It makes different kinds of plasma. Then we have to get that plasma out through a number of different processes. And then at the end of all of that, then we have to do continual acceleration and energization to continue to accelerate that solar wind. And so this is sort of like low down energization and high up energization, and then how the mass gets out. And depending on how you come from here down and which combination of these that solar wind parcel chooses, the solar wind will look very different. And so we think this is why you get different types of these structures in the solar wind. It depends on kind of what type of solar wind the sun makes. All right, back to those structures coming off of our quiet sun helmet streamer here. There's a current sheet out here, which is where that reconnection is taking place. Okay, so we looked at the coronagraph and we measured the time series at each pixel. And at each pixel, we tested for periodicities out in the solar wind. So this is sort of 2.5 to 15 solar radii. And what I'm showing here are maps of whether or not a periodicity occurred as a function of frequency. So just yes or no, did the frequency occur? Black meaning no, frequency did not occur. White meaning yes, the frequency did occur. So here in our 12 to 4 hour bin, a couple of random hits, but really nothing systematic except at the occulter disk, at the edge and at the occulter disk, which means that there was some sort of little instrumental thing going on there. And then 4 to 2.5 hours is just pretty randomly distributed. So no particular periodicities occurring. Same with about 2.5 hours. And then about at 90 minutes, so kind of broadly between 100 minutes and an hour, we get a concentration of periodicities at the heliospheric current sheet. And we tested the time series at each pixel individually, but you see that this concentration is right where those helmet streamers were. And this, I'm not showing it, but we did look at the magnetic field, and this is exactly where that current sheet is. So something about the heliospheric current sheet makes periodicities at about an hour, 90 minutes or so. And going back to our magnetosphere event, an hour was the longest one that we're seeing. We don't yet have the resolution to look for these in those white light data, but in those data, we were able to find that 1 hour periodicity. It seems to be associated with the heliospheric current sheet. And here what I'm showing is an event in the solar wind upstream of the magnetosphere before one of these events was being driven. And we saw in the elemental composition a 90-minute structure. That's what I'm showing on this panel right here. that in the elements, the elemental composition, there was a 90-minute structure. Now, because the solar wind is collision-less, once it gets to about 2 or 3 solar radii, the elemental composition freezes in and doesn't change as that solar wind advects out. So when you see these elemental composition changes, we know that those were formed back at the sun. Again, this tells us that it was this reconnection process back at the sun that made these structures. And then they survived all the way to the Earth where they drove magnetospheric dynamics. All right, but we can do this because we have the elemental composition. We know that it came from the sun, but we can't watch them all the way out. We don't have the resolution to watch them all the way out. And we can only do it for these very longest events. We can't do it for these shorter scale events. Okay, so that brings us to the 5th question, which is, we made these structures. We know the sun is making structures. And then we also see structures that are impacting the magnetosphere. But we don't know how many of them are, does the sun make them all the time and only some of them survive? Or do they evolve on the way? Or do they combine or merge or split apart on the way? So what is the origin and how do they evolve? How do these structures, these mesoscale structures evolve? I'll mention briefly how Parker Solar Probe is addressing this question. Parker Solar Probe, this is the spacecraft here. Parker Solar Probe launched in 2018, and it used Venus gravity assist to get very close to the sun. And so here I'm showing the orbits that launched from the Earth, and it uses Venus gravity assist to get close to the sun, closer than we've ever gotten before. And here I'm showing the orbit relative in solar radii, and you can see that now that it's getting, it's going to go about to do its last Venus gravity assist, and it will get to 10 solar radii. So closer to the sun than we've ever been before. But if you remember back to those images I showed earlier, still in that collisionless plasma and still nowhere near to the energization that's happening low down in the corona. Okay, but Parker Solar Probe has an instrument WSPR that takes white light images like the coronagraph images, like you see during a total solar eclipse too. So it's just the electron density. And so these are some movies from the WSPR data from these imager. And hopefully you noticed all of the structures coming off here. And indeed, when we go look at the periodicities in these structures, we are finally starting to see some of those smaller scale structures, because WSPR has some special runs where we're able to resolve smaller scales than we had been before with the other instrumentation. But WSPR is a pretty small field of view. It doesn't see a lot of the heliosphere. So the next mission I want to talk about is PUNCH. This is the mission that is in development right now. I'm the mission scientist. PUNCH stands for Polarimeter to Unify the Corona and Heliosphere. The corona, of course, is the solar atmosphere, and the heliosphere is this bubble carved out by the plasma coming from the sun. And the polarimetry is important because the fact that it's polarized light actually tells you whether the emitting structures are close to you or far from you. And so especially for the coronal mass ejections, it helps tell you whether it's coming towards you or going away from you. Okay, this is a cartoon showing the orbital configuration. PUNCH consists of 4 spacecraft that are in low Earth orbit. So here's the Earth, and here are 4 spacecraft. And here they're imaging this cartoon version of an explosion of the sun. And the point is that all 4 of the telescopes look at the sun and look at all of the space around the sun. Here's another version of it where you're seeing the 4 spacecraft orbiting the Earth. And because they're all in different places around the Earth, one imager will be looking at this part of the sky, and one imager will be looking at that part of the sky, and one imager will be looking at that part of the sky. And together they paint out a much bigger picture of the sky than we've been able to paint out before. All right, and so the science questions are basically a lot of what I've been talking about, seeing this mesoscale structure as it advects all the way through the inner solar system. And the key is this, this movie that I showed earlier, taken with stereo, where you see all of this fine scale structure, both spatially and in time, that region of space that covered is this little teeny tiny box here. This is what stereo has been able to take images of, is shown in the blue and the gray here. I think Earth is like right here. But the point is that we only get this very high resolution imaging of the solar wind just very close to the sun. The blue images, which are still white light, these blue boxes, though we only get those images about every 30 minutes, and stereo B isn't even around anymore, so we only get half of these images. And then these ones take so long to integrate. They're like an hour. I think we get cadence here an hour and very low spatial resolution. And then the black spots are up here and down here because we don't have images there. But Punch is gonna, by combining the images from all 4 of the spacecraft, it's gonna fill in this entire region here at very high cadence, very high temporal and spatial scales, so that you can actually see these structures and watch them as they advect through the inner solar system, and watch whether they get broken apart, or watch whether they combine, or watch whether actually kind of the way they're set in the beginning is how they survive all the way through the inner solar system. Okay, and back to the magnetosphere. These structures that look small in the images, the solar system is a big place. And so these structures that look small in the images are actually still big compared to Earth's magnetosphere. And that's why it's so important that we understand them and that we are able to predict them, because of this driving, this daily driving that they do to the magnetosphere. This little blue dot here is the day side of Earth's magnetosphere to scale compared to these structures that are continuously coming off of the sun as the solar wind is created. Okay. So back to the magnetosphere, I'm here showing another one of these events where we had these periodic structures in the solar wind density, compressing the magnetosphere periodically and driving these waves, and the magnetosphere is lighting up. And what I'm showing here, these are maps again of ground magnetometers and separated by frequency bin. And when you see a whole lot of black dots light up, that means all over the globe, the ULF waves, the ultra low frequency waves, were directly driven in this band, and they all saw it all over the Earth. Here, this band just went, so right now the 2.4 to 2.9 millihertz waves are being seen all over the magnetosphere. And then I think we see, yeah, another one go up here. So there's this large scale driving of the magnetosphere, and then there's this shorter scale driving that's showing up at these higher frequencies, directly driven in all of these cases by frequencies that were in the solar wind density to begin with. So that's what's causing the driving. And again, this is a period where actually there was not a big coronal mass ejection, no big solar flares or anything like that. This is all from just the regular old solar wind doing all of this driving. And our work was led by Simone Di Matteo, who's a postdoc in our group. Another postdoc in our group, Samantha Wallace, took that event that we identified and looked at where on the sun did it come from in the first place. Now, as I said, we don't have the resolution right now in imaging to be able to follow those structures all the way to the Earth, but we can look at the sun and ask, where did they come from? So if you're familiar with magnetograms and back mapping, that's what this is. If you're not, don't worry about it, because I'm going to show you over here what Samantha found that we were mapped to. She found that those periodic density structures all mapped to this active region up here. So this active region up here, it's a decaying active region, and we're actually mapping to this spot of pretty unipolar field here. Then we cross the heliospheric current sheet, and we don't see any more periodic density structures impacting the magnetosphere. That whole interaction turns off. And that active region where we aren't seeing any periodic density structures is this one down here. So in red, this active region down here either didn't create periodic density structures or didn't create them in a way that they survived to the Earth. And interestingly, this active region is a very different kind of active region. It's multipolar, so there might be some different dynamics going on. So this is the kind of thing that now our team is set up to do in a statistical sense and see if there are any patterns to the dynamics in the active region and its ability to create density structures. So I talked a lot about driving of the magnetosphere. One of the really cool things about those structures that are between about 1 and 4 millihertz is that they're drift resonant with the radiation belt. And so I'm showing here the Van Allen radiation belt. So those periodicities of kind of 5 to 10 minutes are drift resonant with the particles in the radiation belt as they go around the Earth. And so we have a graduate student looking at this. So again, we have an event where there were no coronal mass ejections, no big storms, and yet the radiation belts are responding to these periodic structures that are driving these waves in the magnetosphere. So here I'm showing Van Allen probe data. And what we're seeing is we're going through the outer belt. This is the slot region. Then we come through the inner zone, back into the slot region, and then back into the outer belt. And the outer belt has these periodicities, the periodicities that we found driving in the solar wind that drove ULF waves, ultra low frequency waves in the magnetosphere, now are causing pulsations in relativistic almost particles in the radiation belt, but all the way through the radiation belt is seeing these pulsations. So we've got a graduate student whose thesis is going to be to unravel exactly which mechanisms are at play here. And in fact, this was one of the events where we saw not just these pulsations in the radiation belt itself, but we saw particle precipitation. We saw those radiation belt particles being scattered and coming down into Earth's atmosphere. Okay, so we do not yet have the resolution to track some of these higher frequency structures that are impacting the magnetosphere to see exactly where they come from, but we have some circumstantial evidence that maybe it's being driven by periodic reconnection down at the sun. So here I've got a cartoon occurrence distribution where I'm showing those sort of 1 hour periodicities that now we do know where those come from. Those seem to be coming from the helmet streamers, the heliospheric current sheet, those sort of that longest loop disconnecting and periodically releasing these structures. These ones, it was hard to tell, but we've analyzed 25 years of wind data, counted up all the periodicities we saw, and we've looked at the alpha to proton ratio, which is one of these elemental abundance ratios that gets frozen in back at the sun. And so it doesn't allow us to watch the structures, but at least we can say, yes, that structure came from the sun. And so what I'm showing here is the occurrence distribution that are contained in these alpha to proton variations. So we know these ones came from the sun. And there are discrete periodicities that show up, but there's also this broad enhancement kind of between 1 and 3 millihertz that it's circumstantial evidence, but it matches very closely with the occurrence distribution of periodicities found in alphanic oscillations, transverse motions seen in the corona. So Richard Morton did some work, and I'm showing the results over here. He looked at the transverse motions of all of these field lines, and he found whether you're in the coronal hole, quiet sun, or active region, the transverse motions of these field lines have this sort of 1 to 3 millihertz periodicities. So we're speculating that those transverse motions are driving reconnection events and making this second distribution of periodic density structures, periodically releasing solar wind out, periodically releasing these density structures out to the solar wind. All right, I think I have maybe 1 more minute, 5 more minutes. Okay, so I will end with one last thing, which is a new mission concept that we're working on. I showed you a little bit of Parker Solar Probe data. Parker Solar Probe at its closest approach will get to 10 solar radii. But as I described earlier, this plasma out here is collisionless, whereas the plasma down in here is collisional. The magnetic field out here is more or less radial, where the magnetic field down here is highly complex. So this is even though Parker is doing amazing things, this is a very different plasma environment than the plasma environment out here. And importantly, it cannot tell us how this closed magnetic field is being energized. So what we're imagining is Huygens probes, and we've named it Huygens probes at the sun for now anyway, to evoke the image of the Huygens probe that was on Cassini. So Cassini had its parent spacecraft and it launched a Huygens probe down into the atmosphere of Titan. And it measured the atmosphere of Titan the whole way down in situ and had amazing measurements. And the key was, because it was this probe that was deployed from the parent spacecraft, it didn't have to live that long. And so what we're imagining is a parent spacecraft that is on maybe a Parker-like orbit and gets to 10 solar radii and deploys probes into the closed field region of the sun. And we have a project to collect all of the latest advancements in engineering and so forth. And we believe that we can get probes down to 1.5 solar radii, which is where I'm showing here, where you can actually fly through and measure directly the closed field plasma of the sun. Okay, so then I will finish. This is the big takeaway that I hope I got across, which is that the details of the energization low in the corona and the details of higher up in the corona, how that solar wind is released, matters for the types of solar wind structures that are created. These dynamic processes create all these different types of solar wind structures. Some of those solar wind structures are incredibly important for just the daily driving of the magnetosphere. This constant buffeting drives dynamics in the magnetosphere and the radiation belts 4 days after it was created back at the sun. Thank you.
Thank you very much indeed for that Eddington lecture. I'll invite questions. I'll start with one of my own, if I may, which is, do you really have no idea what these bottom of these flux tubes, something is heating and the mechanism there? You say you didn't commit yourself at all as to what's doing that. Do you have?
Yeah,
you must have an idea.
I do. Well, okay, it's the magnetic field. We know it's the magnetic field. That's ultimately where the energy comes from. Those magnetic fields are rooted through the atmosphere down into the photosphere. They're being tangled and wiggled all the time. Probably in the closed field corona, it has to be magnetic reconnection to explain the amount of energy we see. Maybe in the coronal holes where the magnetic fields are open, waves could be doing some of the energization.
Okay, but it's on such a scale, you haven't got any observational thing that you can get in there.
We cannot see the direct energization.
Even if we send you in one of these high, oh, never mind.
If we went with a Huygens probe, then we could.
Actually, there are observations of magnetic fields in the solar surface coming together and opposite polarity and cancelling. We used to think that these were just few and far between, but the latest observations show that they are extremely common. And so those, I think, are likely to be good candidates for generating the coronal heating.
Thank you. Next is one online here.
I've got a total of 3 questions online.
We'll take 2 of them for the moment, then we'll come back.
The first one comes from AC, and it's, do the dynamics of the solar wind effectively change to specific typical structures in resonance to the sunspot cycle, or is it uncoupled from the 12-year cycle?
Yeah, so that's why I showed that plot separated into 11 years. There does seem to be a correlation. The frequencies seem to evolve with the sun cycle. We're not exactly sure why. A big speculation, but my current thinking is that because the coronal loops change as a function of solar cycle, because the type of whether or not you have an active region and those loops will be shorter versus whether you only have those longer loops that are the helmet streamer loops versus the complexity of the active region and whether you have a mix of shorter loops, that those loops will find resonance with different parts of that broad spectrum that's being pulled in. And that's why you get maybe particular discrete frequencies that seem to change with the solar cycle, but we don't know.
Okay, and the second question?
And the second question comes from Messiah Ravichandran, and it's, what's the earliest point in a solar wind's lifetime that we can identify whether it reconnects or not?
Right, okay, so Yeah, when, so Eric described actually, that low down, we see this evidence of reconnection. And then sometimes you can tell that it made it out and sometimes you can't tell that it made it out. In fact, a lot of times what happens is you'll see something happen low in the corona, in the ultraviolet, and then the signal falls off and you have no idea whether it made it out or not. So there's speculation that that was maybe a reconnection event that created the solar wind, or maybe it just fell back down later. We don't know. It's hard.
Okay, we'll come back in a minute there. In the room.
Thank you, Garth Barber. Thank you very much for a fascinating talk. Is there any difference between the activity in the sort of solar equatorial plane and the poles, or are the poles sort of totally different?
Yeah, that's a very good question. Okay, so let's see. I have a couple things to say about that. The first thing is that picture that I showed that was very simple and the poles were very different from the equator was done during solar minimum. During solar maximum, the structures get all turned up and around, and the poles also have complex structures. But so just taking that solar minimum case, yeah, one of our projects is to look at the Ulysses data as it goes over the pole to see if there's any differences there in the types of structures that are being created. As solar orbiter gets up out of the plane, that's something we can start looking at with those data as well. And then punch, which will be able to image over the poles, will also give us some information about that. But right now, the imagers that we have, the white light imagers, are only in the ecliptic, are only at the equator, so we can't see.
Any more questions in the room? Yes, John Zarnecki.
Thank you very much indeed for the talk, which I'm sure everybody enjoyed. However, I feel as one of the original Huygens probe experimenters, I do have to record an objection.
Oh, no.
I think we have a copyright on the name.
Okay, all right. Okay.
Huygens 2 is the another question from online, please.
Thank you, Sue. This question has come again from Mathaya Ravichandran, and it starts Q1, but we don't have a Q2 yet.
Oh, depends on my answer. Okay.
Is there significant gravitational interaction like waves caused by the high speeds solar wind? If it causes, what can be the magnitude that can be expected from them?
Gravity waves from the high speed streams? I don't think so. No.
No is the answer, right? Any more questions in the room? There's one here.
Hi, Steve Schwartz. So I have a question about this, Van Allen, about observations that you made. Are you suggesting that there's more than just kind of compression as you go back and forth across the gradient?
Yeah.
Does the energization go in phase or out of phase with the external driver, et cetera, et cetera?
Yes, that is Lena's thesis project, because
I want to spill the beans, that's what you're saying.
well, no, it's actually quite complex. Sometimes you see energization, and then sometimes you see the radiation belts get depleted. And why one versus the other, we don't know yet. And it probably has to do with steps along the way. It's probably not enough to get the driving. Might be that the waves then lead to chorus or hiss waves, which are a different type of wave, and then those do the scattering. So that's Lena's thesis, is to figure all that out. Yeah.
And the heating is more than just kind of adiabatic compression?
So that was one of the, well, right. We saw particle scattering in this event. So it's not just adiabatic compression, but yeah, if you just see the pulses in the radiation belt only, then it could just be that. But because we saw the particle precipitation, we know there's more going on. Also, sometimes you can get magnetopause shadowing where because of the original squeezing, some of the ones on the outer drift shells go away that way. So there's actually quite a few different things that can happen to the particles. Yeah.
Okay, any more in the room? No? Well, thank you very much indeed.